All right, STAT1150. The purpose of this video is to introduce you to something called Z-scores. And, um, again, I told you early on, I've taught this class, a lot of times, many times. And I found that of all the content in the STAT1150 curriculum, Z-scores tend to cause the most confusion. So I'm going to take a completely different approach at teaching Z-scores in an attempt to minimize the level of confusion for z-scores. So, uh, I'm not going to get into the weeds here, but let's proceed, and we'll see how it works out. Okay, so key concept in stats is to determine the quote unquote location of a data value. And questions that we ask ourselves, is it the score above or below the mean? And then we would want to also maybe address how far away from the mean the data value is. And one way to do this to assess location is to use the z-score. Now, another way we can do that is called percentile ranking. And once we get into the normal distribution, the normal probability model, in lesson 3, we'll get into percentiles. But for now, I just want to keep this simple. And again, coming full circle here, the reason I'm taking this very deliberate approach at the presentation of z-scores, because you're going to see z-scores in this lesson, and you're going to see z-scores again in lesson 3. So I'm going to take, again, a deliberate approach because students historically have struggled with this concept. All right, enough of that. So a z-score is a standardized score, and what it does is it tells us how far away from the mean a data value is based on the number of standard deviations. So in other words, how many standard deviations above or below the mean is this particular score. So we calculate the z-score using the formula that you have on your screen. So the z is x. X will just be the score that we're trying to determine the location of. The mean, x bar, is the mean of the distribution from which that score came, and S is the sample standard deviation. So all we're doing now is we're just evaluating z-scores for sample data. Again, we're going to change this to population data once we get into lesson 3, but let's crawl before we run, okay? Uh, so rounding rule for z-scores, always round to 2 places. So if you have like 0.81, it would be 0.81. If you have negative 1.27, you have negative 1.27. Important properties of z-scores. Again, a z-score is the number of standard deviations that a given value is above or below the mean. If z-scores are positive, big stuff here, make sure you tattoo this into the brain. Very important. Positive z-scores indicate that a score is above the mean. A negative z-score indicates that the score is below the mean. Um, z-scores are standardized units, so there's no unit of measurement. And we have these cutoffs that define a significantly low or significantly high score. So if a score computes a z-score which is greater than 2, it's significantly high. If a score computes a z-score that is less than negative 2, well, less than or equal to technically, then it's a significantly low score. I think this is all going to make a lot more sense once we start crunching the numbers. So uh, let's compare ACTs and SATs, two completely different scales. And it's really hard to compare them because, again, they're on two completely different scales. So let's say that we have an ACT of 26 that was calculated among 106 students with a sample mean of 22.5 and a standard deviation of 5.5. We also have a group of 140 students who took the SAT. Their mean was 1247, sample standard deviation 188. How does a score of 1400 what's the location of an SAT of 1400 in this distribution? And then what we can do is we can compare the two scores, the 1400 versus the 26. Well, the solution here is to convert each to a z-score, a standardized score, so they can be compared. So you can see the calculation I've done there for the 26 ACT. I put 26 in for X because that's the data value we want to calculate the z-score of. I put 22.5 in for the mean, and I put 5.5 in for the standard deviation. Rounding to two places, I get 0.64. The SAT of 1400, same logic. 1400 is my X. 1247 and 188 are the mean and standard deviation respectively. The only thing I can tell you is make sure you put this in your calculator correctly. I would put left parentheses, for example, for the SAT. I would put left parentheses 1400 minus 1247, right parentheses, and then divide by 188. If you don't do that, you're going to get into an operation error and order of operations error, and you'll get the wrong z-score. All right, so what do both of these tell us? This tells us that an ACT score of 26 is 0.64 standard deviations above because it's positive. The mean, an ACT of 1400 is 0.81 standard deviations above, again, because 0.81 is positive, the mean. Now, because the SAT is further above the mean than that's a little choppy there, isn't it? So what I meant to say is because the SAT is farther above the mean than the ACT, then it is, a higher score, relatively speaking. However, neither score is above 2, so or below 2 for that matter. So neither one is considered extreme or significant. IQ scores are calculated on 32 randomly selected students. We have another example here. Mean IQ is 103.5, standard deviation 16.9. Calculate and interpret the z-score for an IQ of 142. 142 is a big old whopping IQ. That puts you up in genius levels. So we're expecting a pretty high z-score. So again, same song and dance. Insert 142 in for X, minus the mean, divided by the standard deviation of 16.9, and I get 2.28. So I conclude that an IQ of 142 is 2.2 standard deviations above the mean. We can even go further and say since the z-score is more than 2, higher than 2, standard deviations above the mean, then an IQ of 142 is considered significantly high or an extreme value. Gestation periods calculated on 32 randomly selected women. The mean gestation period is 266 with a standard deviation of 16 days. Calculate and interpret the z-score for a gestation period of 225. Well, as you would expect, we're going to do the same thing. We're going to put 225 in for our X, 266 is our mean X bar, 16 is our standard deviation. Doing the mathematics, or actually just the arithmetic, we get negative 2.56. So we conclude that a gestation period of 225 days is 2.56 standard deviations below the mean. Why below? Because it's negative. Since the z-score is more than 2 standard deviations below the mean, negative 2.56 is further down than negative 2. We can say that 225 is considered significantly low. Now, which is good, a positive z-score or a negative z-score? Well, it depends. If we're looking at cholesterol levels, then hey, sign me up for negative z-scores every day. If we're talking about, I don't know, family income, then, hey, sign me up for a very high Z-score. So it all depends on the relative nature of the problem that is being examined. All right, so just a visual. How do we identify significant values? Again, less than -2, we get significantly low. And these are all Z-scores, okay? Significantly high values, Z's greater than 2. Anything between -2 and +2 is considered not significant. That's going to play a major role once we get into hypothesis testing. I think in lesson number 6, we're going to get into statistical significance, whether or not our test is statistically significant. And this gauge of 2 and -2 is going to circle back. Okay, final example. Is an earthquake magnitude of 4.01 significantly high? Well, this is from data set 24. So we see that the mean is 2.572 and a standard deviation of 0.651. So what about the magnitude of 4.01? Well, we're going to calculate the z-score. When we do that, we get a z-score of 2.21. And because 2.21 is higher than 2, then we say that the magnitude is significantly high. Well, that's about all I have. Again, there's a lot more to z-scores because they form their own distribution with their own mean, their own standard deviation, their own standard error, lots of fancy stuff. But I want to, unlike what I've done previously, I want to just introduce z-scores in a small manner, and then we'll get into some fancy stuff later. So I hope this helps. That's all I got. Take care.